In the last lecture on Fortran, that is in Fortran-11, we have introduced the Fortran subroutine. Now we shall use this subroutine. We shall discuss our continue our discussion on Fortran subroutine. As the next example, we consider radial probability distribution. RDF, which is known, and it is defined as DNL of RDR is equal to R square R NL square RDR, where it is the radial wave function. RNL is the radial wave function of hydrogen atom, and DNL is the radial probability distribution. This gives you the probability of finding the electron within a spherical shell of radius r to r plus dr in a state designated by n and l, principal quantum number n, and the orbital angular momentum by quantum number l. We want to find out this DNL for the lowest 6 states, that is 3p and 3d. So the plan is to find have values of r from 0 to some particular value a, and to have the DNL for each of these 6 states. So this is the plan of the program. We define this so read star comma star n and a. So a is the maximum value and n is the number of steps in which we want to span the space from 0 to a. So it is the maximum value, max r, and it is the number of sub-interval, number of points between 0 to a. So we first defined h step size is equal to a by float n. Then do blank 5 blank I is equal to 1 to n. Now we first define r. R is defined as h times I minus 1. So when I is equal to 1, it is 0, and when I is equal to 1, this is h, and so on and so forth. Another thing, this is better to write it than it is simply float I. So it is 0 at I is equal to 0, and it is a at I is equal to n. A is to be determined suitably. Now having been defined, we will call subroutine call blank RDF radial distribution function. It will have first r and the outputs for S1, S2, P2, S3, then P3 and lastly D3. So there is only single output R and a single input R and 6 outputs. Then we write five continue. This is the main program. Now coming to the subroutine. If we first define R1s, the wave function, R2s. Let me first define R1s. R1s means radial function. R1s is given by 2.0 exp minus R. R2s (1.0) this is within bracket, then 1 point minus R by 2.0 star actually R1s is this. R1s is 2 e to the power minus R. R2s is equal to 2 times 2 upon square 2 into 1 upon 2 to the power 3 by 2, 1 minus R by 2 e to the power R by 2, R2p. R2p is 1 upon root 3 3 by 2 R times e to the power minus R by 2, R3s (3 to the power 3 by 2), 1 minus 2R by 3 plus 2R square by 27 e to the power minus R by 3, R3p 4 root 2 by 3, 4 root 2 by 3, 1 upon 3 to the power 3 by 2 R into 1 minus R by 6 e to the power minus R by 3, and finally R3d is equal to 2 root 2 27 root 5 1 upon 3 to the power 3 by 2 r square e to the power by r by 3. So you can define other things similarly. So there are 4 more lines which I am skipping, and you can write ultimately this is R3D. Now we define S1 is equal to R times R1s whole square. S2 is equal to R times R2s whole square, and similarly other definitions. Ultimately you will land up with D3 then return it. So in this subroutine, what we have done, the R is supplied, then within the subfunction we have defined the radial functions for the first 6 states of hydrogen atom. Then we have defined the radial probability distribution as this. So these 6 are the outputs and this is the program. So this is a simple example from chemistry point of view. As the last example of subroutine, we consider a subroutine which will calculate whether two given matrices or two square matrices of same dimension, so that there are two matrices A and B, both are square matrices of dimension n, and so the program will check whether they commute or not. This is the program. So firstly we read the dimension of matrix n. So we are considering two matrices n cross n, another matrix B n cross n, and our aim is to calculate the AB commutator. What is this, 0 or not? So the program first dimension of AB, these are the two matrices. This is the dimensionality of the matrices. Matrix A. IR is equal to 1 comma n. These are known to you as has been explained in the in case of matrix operation. Do blank 1 blank, then write star comma star entire thing, 1 continue. This will read the matrix in matrix form and will write it in the same. Then we run this, copy this part for B, matrix B. The changes are, I am underlying the changes that has to be made for B. Change it to a suitable number, say 2. Then this A will change. You write this, change this, and this will also undergo a change. So it reads the matrix A and B. Now we call the subroutine, call blank name commutator with A, B and index. Index will be returned. We set the index in such a way, if it is 0, then the matrix commutes, and if not 0, then it doesn't commute. So this part I am being incomplete. First I am going to the commutator and then comes to this. Blank first dimension, same dimension has to be supplied, otherwise the function won't work. This is customary because the calling main program has this dimension. Apart from this, I will need for another dimension. We define C matrix is equal to AB matrix and D matrix is equal to BA matrix. So these two dimension has to be so. If there were space within 72 columns, you can write this here with commas. Oh, another thing that is not given, sorry for, n has to be supplied. N has to be supplied. So it should be now the now we have to do the C. If C is equal to AB, then Cij is equal to sum over K, Aik, Bkj. This part has to be completed. So first is do blank 1 blank IR is equal to 1 comma n, do blank 2 blank IC is equal to 1 comma n. This IR IC with this 1 2 will not conflict because this is in the main program and this is in the subroutine. Then within this we define CIR IC is equal to 0.0, DIR IC is equal to 0.0. This is the initialization. Then we define do another loop, do blank 3 blank IK is equal to 1 comma n. CIR IC is equal to CIR IC plus A IR IK star B IK IC, and for D, IR IC is equal to D IR IC plus B IR IK star A IK IC. Note that C is equal to AB, that is Cij is equal to sum over K Aik Bkj. This is done in this line, and D is equal to BA, that gives Dij is equal to sum over K Bik Akj sum over J. This is, and for executing this sum, we have always written sum is equal to sum plus term with proper initialization. These are the initializations, and so now the task is to complete 3 do loops in order. First 3, then 2, then 1. Now we are to check whether this these two matrices are equal or not. If they will commute when they are same, so we may use another loop, or we can do it here also, but I am doing another loop. I am setting index is equal to 0, and if we calculate these quantities, there may be truncation error. As for example, 1.3 may not be look like this, that is 0.3 recurring. It may so happen that it is 3, 3, 3, 3, then 8. Oh, sorry, 2. This is the truncation error. So due to this truncation error, even if the elements are equal to each other, there will be a difference after certain steps. So they will not be 0 as. So we define 0 like this. Is equal to, say, 10 to the power minus 6 as 0. So in our practical purpose, if a quantity is less than 10 to the power minus 6, will be considered as 0, and if it is greater than this, it is non-zero. Here is another difference from analytical mathematics with the computational scale. Then do blank 4 blank IR is equal to 1 comma n, do blank 5 blank IC is equal to 1 comma n. We calculate T is equal to CIR IC minus DIR IC. If ABS of T is greater than 0, we redefine index as IND is equal to IND plus 1, and then the 2 loops are completed. 5, then 4. Continue. then return it. Let me explain the working of the program. It compares all the n square element. IR is equal to 1 to n, IC is equal to 1 to n, so n square element. It first calculates T as the difference of C and D. So T is the T is the actually Cij minus Dij. Then we calculate the absolute value of T. If absolute value of T is greater than our defined 0, then index is redefined by as index plus 1. If the two matrices A and B commutes, this condition will never be satisfied and index will remain 0 as we have defined here. It is an integer quantity. So the function returns index. So what we call? We do it if I and D 0, because it is integer, so then A and B commutes, else do not commute. There is one more advantage of writing program via subroutine is that the main program is this much and entire moderation has been put in the subroutine, so we can check the two units separately whether they are correct or not. That's all about subroutine, and when we shall go to the actual problem that has been described in your syllabus, we shall encounter many more examples on Fortran subroutines and subfunctions. In the next class, I will give you some idea about the iteration in numerical calculus, in numerical analysis, or the process of iteration as used in numerical analysis.